Hello and welcome to the series of lecture in VLSI design. So our first lecture is on MOS transistors. So to understand these MOS transistors, we would first like to know what a MOS capacitor is. So a MOS basically stands for metal, oxide, and semiconductor. Basically, there is an oxide layer which is sandwiched between a metal and a semiconductor layer. I'll just draw a diagram to make it more intuitive. So let's say this is a metal layer, this is a very thin another oxide layer, and then there is a third bigger semiconductor layer, all stacked on top of each other. Now, this metal layer, the topmost layer, is mostly made up of polysilicon, which is a crystal form of silicon, and it is a good conductor of electricity. This middle layer, which is this one, is actually made up of silicon dioxide or SiO2. And the third layer, the bigger one, is a semiconductor. It's a semiconductor. It can be an N type or P type. This is also called substrate. Now, to understand the working of this MOS capacitor, let us consider it like a normal capacitor which has two metal plates. If you recall from your basics, capacitor is consisting of two metal plates and a dielectric in between. So this will act in a similar fashion and will have three region of operations. These three region of operations are accumulation, depletion, and inversion. So we'll discuss all these regions in detail now. So let's do one thing, just copy this. Let me copy this whole thing and paste it over here. Right. So if we connect this top layer with a battery, the metal layer with a battery, and we apply a voltage, which is a negative voltage, what will happen is, suppose this substrate is of P type. So when I say P type, what it means is that it has abundance of positive charge carriers, right? So what will happen is, if you apply a negative voltage here, this Vg is less than 0, that means the positive charge is accumulated towards the SiO2 layer, towards the insulator, right? And because of this positive charge, there is some negative charge induced on the top side. So this is behaving exactly like a capacitor would behave. And this region of operation is actually the accumulation. Accumulation of the majority charge carriers towards the gate. When I say gate, it means this metal layer or the polysilicon layer. Now, so this is the A, that is the accumulation one. Now we come to the B part. Now here we again connect a battery but at this time the voltage is slightly positive. So we say that VG is greater than 0. All right. But actually VG is also not very much large. It is less than, let's say, a threshold voltage VT. Okay. So what will happen is, since this is now positive, all the majority charge carriers that are there in this p-type substrate will be pushed downwards, right? Because there is a positive charge on this plate, so this will be repelled, and there is a void of charge. There are no charge present here. So this is a like a depletion layer. This There is no charge, so we call it depleted layer or depletion layer. Depletion layer. All right. Now we come to the third part. Let me again paste it. Okay, just removing these. Now what will happen in the third part? We are again, this battery is again positive. The voltage VG is again positive, but it is now greater than the threshold that we have defined. Threshold is any voltage, okay? Any arbitrary number. We'll explain in the later series why this threshold is coming. So what will happen is, suppose this is sufficiently large, and of course, there are positive charge carriers in the p-type substrate here. This is p-type, but there must be some free electrons also, though in minority, in this p substrate. So those electrons are now getting attracted towards the oxide layer. So these are the minority charge carriers that are present in this p-type substrate, which are getting attracted towards the oxide layer. So what is happening here is, there is an inversion from accumulation to this C part, that is inversion of charges. Earlier, if you see, they were all positive charge. Now there's an inversion, and we call this an inverted layer or inversion region. Inversion region. All right. Okay, so now if this much is understood, you have understood the concept of a MOS capacitor. This is behaving these three layers sandwiched on top of each other, is acting as a capacitor, and we call it as a MOS capacitor. Now, using the same concept, scientists have developed another device called a MOSFET, or metal oxide semiconductor field effect transistor, or a MOS transistor, which is slightly modified, but it is working in a very similar fashion. So we'll draw a MOSFET diagram now. MOS transistor. All right. So what's happening now is, we again have a top layer, which is a polysilicon. Then we have a small oxide layer, and then we have a substrate, as explained earlier, right? Now here we have two more regions which are like this. So again, if we recall, this is the polysilicon, this is silicon dioxide, this is p-type substrate, or the p-type body. This is a highly doped N well, the N regions, and we call them source or drain. Let's say we call it source, we call this drain. source, drain. Now, let's say, let's say we apply this body, we call it body, right? So this body is always kept at ground. Let's say we are keeping it ground for the time being at least. Now this is the gate, what we call gate. So basically there are four terminals, right? We have a source terminal, we have a drain terminal, we have a gate terminal, and we have a body terminal. We are connecting the source to the body like this, okay? And let's say we apply a very small voltage, which is VGS, right? This voltage is VGS. So as long as this voltage is zero, we don't have any inversion layer here, right? All this, everything is positive, positive, because it's a p-type substrate. So this we call cutoff region. There is no inversion layer, therefore there is no current. Now, if we take this diagram again, let me just copy this. And we apply some potential between the drain and the gate as well. So what's happening is now that we are saying that VGS now is greater than zero, all right? And VDD, that is the potential between the gate and the drain, is zero. Sorry, it's VGS, which means that the VDS, the difference between drain and source, is zero. But what's happening here is these electrons, this positive charge will not be there now, as we have seen in the MOS capacitor. There will be an inversion layer now, and we'll have negative channel formed between the source and the drain. All right, but because the difference between the drain and the source right now, VDS, is zero, there is no current. So even though this there is a channel formation, the current will only be there as when there is a potential difference between the source and the drain. So now what we'll do, we'll start increasing this VGD, okay? So that there is a difference between source and drain, and VDS then will not be equal to zero. There is some VDS, and what will happen? The current will start flowing from the source to the drain, all right, because the electrons will start moving from drain to source. So right, so the electrons will start flowing from source to drain, and therefore the current will be flowing from drain to source, right? So this region of operation of a MOSFET is linear region, okay, right. Now let's say we keep on increasing this value of VDS. So at one point, what will happen is the, the capacitor which was forming near the drain is no longer inverted. So what will happen? The channel will look something like this, right? So the current will not increase after a certain point because there is a pinch off. and the current becomes saturated, and therefore we call it as a saturation region. So instead of linear, it will be saturation. Now, there is an obvious doubt that why, if there is no channel near drain, then how come the electrons are still flowing from source to drain and current is still flowing? The reason for this is due to the drift of electrons. So there is an electric field, right, between the drain and the source. So even though the conduction might not be possible because the channel is not there, because of the drift, since electrons already have a drift because of the channel near the source, so because of that it will still be flowing towards drain and the current is still flowing, but it will not increase if you keep on increasing VDS. So after a certain point the current saturates. Now, and this is the saturation region. So now we have discussed three regions of operation, that is the cutoff region, the linear region, and the saturation region. So this type of MOSFET is called N type of MOSFET. All right. So N type or NMOS, because the source and the drain are highly doped N regions. All right. So for an N type MOSFET, the body is a P type substrate. All right. A similar argument can be seen for a P type MOSFET as well. If somebody wants me to upload a video for P-type MOSFET, do let me know and I'll do that. Okay, all right. So in the next lecture, we'll derive the equation, the current equation of this MOSFET, and we will be able to understand how this current is changing based on the different value of voltages, that is the gate voltage and the drain to source voltage. So let's see everybody in the next video. Thank you.